And now comes the main result. I haven't seen it outside of dynamics, actually, the main result. And I can find some precursors. So there is a Selberg zeta function, which is an honorable part of pure mathematics, in which one has a hyperbolic surface and one tiles it with octagons in the simplest case. And, that's the only place I've seen something similar happening. But here is the result, which is a bit surprising. If you have a prime periodic orbit in this space, so it's a periodic orbit in your world, no matter how complicated. But this one I tried to draw in some sense to have a threefold symmetry as I move around. Didn't succeed, but it could be done. Then every prime periodic orbit in a full state space, if there is a discrete group, so for example, if this was the orbit, it would show up as many times as the symmetry can make copies of it. So that's called multiplicity of the prime orbit. But if the orbit itself has a symmetry, it won't show up as many times. So for example, this orbit, if I drew it, well, when I rotate it, just the same orbit with points permuted. So that one might have multiplicity 1, or definitely this one in the origin has multiplicity 1. So this is a full state space. And this is the multiplicity. So how many copies does the symmetry make of one of them? This is now the product of irreducible representations of this symmetry group. For example, permutation group on 6 elements or something. And symmetry groups have irreducible representations. It might sound mysterious, but I'll first show you that in one dimension with a flip, the space might be two-dimensional because there are two group elements. But irreducible representation are either fully symmetric or fully antisymmetric, so they're one-dimensional. So you have seen at least the simplest case of it. So this is irrep is what group theorists like to say, and also people who do quantum mechanics for a living, old-fashioned quantum mechanics. So label every irreducible representation with a Greek letter, for example, alpha. And this is same as 1 over delta alpha. So I'll spend at least 2 lectures trying to explain what happens on the left-hand side. So remember, what we are doing is we are connecting local information, TP, to global information, which has to do with how we act on the whole state space. And it turns out that this thing can be already decomposed using the symmetry, using the copies on the full space of the original thing, into a formula where this is the irreducible of group G. And the way that it's, finite dimensional matrices showed up was through this identity, that I could split up space into acting on d-dimensional quantities. And then the cycle weight, small trace, is computed only on the relative periodic orbit, which is this segment that's being repeated 3 times, for example. So this is what I'll try to derive. Beginning is fairly sensible. The end looks somewhat mysterious, but it's doable. You will get. And the way I'll try to motivate it is by working out a simple one-dimensional example.